All right, last person between you and ice cream. Little did I know what problems I signed up for when I agreed to speak at my son's third grade career day. He asked me, I said, sure, no problem. I'm an electrical engineer by training. I've been working in the broadcast engineering for the past 24 years. That's where I started my career, and that's where I am right now. I didn't think much of it until I got an email from the teacher with a roster of speakers. If you know me, you know I'm a competitive person, and I always I like putting on a show. So the first speaker, an accountant, easy. Second speaker, physiotherapist. I will comment about that. And I was the last person. However, the third person was Emily's dad, and he's a firefighter. So, like any father who's trying to hold on to the hero worship that their son may a little bit still have of them in third grade, I hunkered down and I summoned my inner Steve Jobs to work on my keynote speech for the third graders. And this is how it went. I explained to them what Black Cat is. Black Cat is one image. And then I told them if we take another image and another and another, and we keep moving that image around, we get video. I explained to them how things start with a camera. If you end up on a screen, whether the screen is their iPad or television or a computer, it doesn't really matter because that's the industry that I'm in. I explained to them that invariably anything that they're looking at has been processed or touched by a computer. So I took a really old workstation. I put some Matrox 2110 NICs in them. I put an SDI card. I put a GPU. I put network cards, and I really souped up the system that would never boot, but it's okay. I took it with me, and in the presentation, we opened it up together. We took out the components. Somebody took out a memory. Somebody took out the hard disks, and so on and so forth. And it was very interactive, a really good experience for me. And what I told them was, what I did is I worked at this layer over here. I worked in the sort of the plumbing area where I've spent all my career building interface cards for professional broadcast. I have also been doing software libraries that what broadcast applications do, and that's what broadcasters do. They deal with applications when they're producing. They deal with CG, replay production switchers, PC-based switchers that live on top of this layer over here. And that's what I did. Some people got to leave with a hard disk. Some people got to leave with a memory stick. So it was a fantastic experience. So why am I telling you all of this today? Because today I want to talk about Black Cat again, because we're going to go back to basics and talk about one of the biggest challenges that we are facing in our industry and how, from a basics perspective, we should be addressing this. So market fragmentation, reduced budgets, et cetera, et cetera. We all talk about this. It's a reality that we have to deal with. So how do you do that? And how do we decide what we're doing when we don't even know what we want to do and there's no business case for it and so on and so forth? This is not what I'm going to be talking about today, but I have a solution. You need to do a lot more with a lot less. Great. Yeah. How do you do that? Well, I say look up to the North Star. The North Star will guide us there as an industry. And the North Star is a public cloud. That's the destination. However, like any wise person would tell you, it's never about the destination. It's about the journey. And our journey is through software. It's our shift towards software-centric workflows. And we may end up at that destination. We may be there right now, or we may never end up there. But we have to go along that journey, and in that journey, we have to reap the benefits of software, whether it's on premises or in the public cloud. So how do we build software architected media facilities? And it's a mouthful. But today what we're going to talk about is, I'm not going to talk about containers. I'm not going to talk about Kubernetes. I'm not going to talk about IT tools. I'm going to go from the basic principles concept of how we do this. This is how we build broadcast architecture today. We have a source. The source is connected from one point to the other, and it's all clock locked. And it sounds like I'm making fun of it, but that's how we do things today. And we use fantastic technology to make this happen. And I'm not actually making fun of it. I love this technology because other than connectivity, it gives us deterministic control and allows us to build large-scale systems. Now, if we want redundancy in this architecture, well, we double everything up. We lock everything together to one master clock, and off we go. We have the source to the destination connected. Now, everything is clock-driven, synchronous. Now, if we look at what an IT infrastructure looks like, it looks like this. We have a source, we have a destination, we have one thing that does work, it triggers an event, the other thing takes over, does its work, and so on and so forth. And that's how everything is interconnected. Now, one thing I can tell you, this is not a well-kept secret, but I've been doing this all my career, is that in these boxes I was talking about before, more often than not, there's a computer. And inside that computer, we're processing in CPUs and GPUs, and we are actually event-based. We are running as fast as possible in there. However, when we interconnect these systems together, we're going through a synchronous interconnect. Baseband synchronous interconnect, whether it's SDI or 2110. So let's dig a little bit deeper into that. The evolution of baseband interconnects. So we went from SD at 270 megabits per second to 12 gig, 11.88 gigabits per second to do Ultra HD. Faster speeds gave us higher resolutions. And I love SDI. It still baffled me how we're able to with one wire drive 100 of meters and still recover a signal at the end that has a clock embedded in it. It's still fantastic technology. Now, as an industry, we needed more flexibility, so we came up with something that's more resolution agnostic. So faster speed give us higher resolutions and or higher density. Now, this table that I'm sharing with you over here is for YCBCR 422 10-bit at different resolutions at different Ethernet speeds. Now, what I'm telling you here is from the perspective of an endpoint. So from an endpoint perspective, everything I've highlighted here in green, in my personal experience, is something that's relevant. So I can think of many different applications that need that level of I/O to actually do the job, to do something that's useful for us, whether it's a multi-viewer, whether it's a PC-based switcher, or what have you. However, on the yellow side, I cannot come up with one example where we need 286 HD flows, inputs and outputs simultaneously to saturate that connection. I don't have any examples. So what we're doing over here is we're no longer capable at these higher frequencies to actually utilize the IT equipment that's there if we stick with asynchronous interconnect. Now, other industries use the faster speed to actually go faster, but what we're doing is we're only able to go larger. And with this architecture, what we can do is that creates a system that has a more monolithic endpoint architecture, which also leads to more to single points of failure, etc. So let's go through a timing diagram. And here I went with I call it a theoretical timing diagram because it's actually quite simplified, but it makes a really relevant point. So we could start with a camera that goes through a synchronous interconnect to blue mixer, another synchronous interconnect to a green mixer up to a screen. So let's look at the timing of how this happens. So here we have mandatory real-time transport coming in. We go into the blue mixer. It's a PC. It runs as fast as possible. We do the work. We're done. Then we have idle time because we cannot output till the next VSync. Then we have a real-time mandatory real-time interconnect. We go to green, run as fast as possible. then we have idle time, and off we go. Now we have our final output. In this example, I'm using 16 milliseconds and a processing time of 4 milliseconds, and there's more information about that in the paper. So let's dig a little bit deeper. So our total into out for this theoretical example is 64 milliseconds, so that's 4 frames into out. In terms of real-time transport, we have 32 milliseconds that are fixed that we have to pay, and this increases per hop. In terms of processing, 2 times 4, 8 milliseconds, and idle time, we have 24 milliseconds. Now, what I want to do is I want to dig a little bit deeper into what idle time means, because idle time for me means opportunity. So let's look at it from a compute perspective. So we have a compute opportunity to actually do more work inside of the blue mixer, and we have a compute opportunity to do more work inside the green mixer. So that means that we could do more processing, we could do HDR conversion, we could do more layers, we could do whatever else we want to actually fill that idle time. But that's a computational incentive to build a monolithic architecture, and that's computational incentive that we have taken as an industry, and we've built this huge monolithic application that we all use and love because there's fantastic technology in there. If you look at it from an opportunity for resilience, what we have in these idle times is additional resilience capability. Should there be a hard disk stutter, should there be a virus scanner that kicks in, well, that's idle time that we can use to recover, because that system is running event-based and we'll just recover because we have idle time. However, these opportunities give us only a monolithic perspective give us monolithic opportunities, because the compute can only happen in blue, can only happen in green, and the resilience that we get from idle time is only applicable to blue, only applicable to green. Now let's look at this from an asynchronous or event-driven perspective. If we get a real-time input, we process as fast as possible. We trigger an asynchronous transport to green. Green does its work. And we have idle time because we can only output at the next vsync. And that, off we go, we have our output. So our into-out delay is 32 milliseconds, so 2 frames into out. Real-time transport, and this is the mandatory real-time I/O, is 16 milliseconds. Processing is the same, 8 milliseconds. We're using the exact same computers. And the idle time is 6 milliseconds. Now, asynchronous transport, the new entity that I created, is 2 milliseconds, and I give an idea of how we got to that. Now let's dig into the idle time. So the idle time, like we discussed, is an opportunity. So let's look at it from a compute opportunity. That's the compute opportunity to do more work that does not have to live within blue or does not have to live within green. It can be available for somebody else to do work for us. As we look at it from a resilience perspective, if there's a stutter from any of the PCs, whether it's blue or green, well, it's accrued idle time that can account for system vagaries. So we have a more modular perspective on the opportunity. So quickly, the comparison, 64 versus 32, reduced latency, increased efficiency. Now, we have to think from the perspective of what does baseband interconnect give us? Well, what it does is it really moves time-sensitive, uncompressed video for us. So if we do not think of it in these terms and we say, well, we need to move time-sensitive, high-bandwidth data, well, unlike what our mothers told us growing up, you're not special. We have many different industries that have solved the exact same problem. But that's okay. We can build our innovation on top of what other people have solved, and from there, innovate within our own industry. So synchronous interconnects are conceptual technologies for glass when real time is mandatory, whether it's a camera or whether it's a monitor. Now, but if we think really deeply about what we do, is actually there's more to it than that, because that's just the tip of the iceberg. What we have is we have deterministic results because of the synchronous interconnect and the nature of it. So what do we need in order to build large-scale systems using what we were talking about before, the concepts? Well, we need to have frame-accurate control at scale. We need to have low latency systems. We need to build responsive systems. When you press a button, you want to see the action happen. Redundancy. We went to lots of, to great realms to protect against every single packet being dropped, clean switching at scale, and building an environment that's observable, that when we operate, we can dig into and operationally determine if a problem happened, when it happened, why it happened, how we can prevent it in the future. And best of breed choice, because we always want to use the right vendor or the right tool for that specific application. So how do we reimagine this whole process? Well, we could start with the glass, the mandatory real-time cameras, and the mandatory real-time monitors. Those pose a real-time constraint on the systems. Control is another real-time constraint on the system. But everything else, when this processing bubble runs as fast as possible and as soon as possible, and we don't really care exactly when it actually runs, as long as it's ready before we need it. So live data comes in and it gets transformed into fields or frames or grains or black cat. We associate a presentation time with all of these grains, and these are associated with real time. So what's the technology stack required to do this? Let's start at the hardware level. This is the compute, EC2 instances in the public cloud, CPUs, GPUs, and fast networking, or on-premises Dell HP servers with professional I/O in them. Well, what we need is a media-aware framework that interconnects all these systems together, and this framework brings scalability, it brings timing, it brings flow of data across these systems, and has resilience in it. In and by itself, the framework doesn't actually do anything. What it needs are media services that actually do work for us. And these media services are either the ones that deal with the real-time world. They could be the software type, like an NDI, CDI, or SRT, or what have you, or hardware services, whether it's SDI or 2110. Everything else in between the media services are isolated. They do one job, they do it well, and they process buffers. They have no concept of time. They just run as fast as they can. And these are specialized. We have different companies, different vendors that have specialized knowledge in these types of processing. So what we need is our APIs to build this processing. Now, we're talking about systems that live in a public cloud or in a data center somewhere else. Well, we need a control application that can talk to these media services, and obviously we're talking about web APIs, and these control applications can provision and control the media service to actually perform a desired function for us. On top of that, to complete the picture of the technology stack, when we talk about large-scale systems, we need to be able to orchestrate these systems and monitor what's happening. And obviously, we need metrics in these systems to know what's happening. And this allows us to automate, measure everything that we're doing. And these are the components that build up an asynchronous media framework. So from a system architecture standpoint, we have controlling application that's web-based that talks through to a server. A server is an endpoint that has knowledge of the whole system. The server talks to hosts, and hosts are actually the computers that are doing the work for us. On these computers, we have pieces of software that interface with buffers, whether it's from the real-time world or whether they're specialized, for example, like a video mixer, an audio processing engine, or what have you. And for this to be more powerful, we need these to be stateless, and I'll talk about that a little bit later. And all of these are interconnected with a transfer fabric to move data around these systems. Now, the transfer fabric in its simplest form, we should think of it more as a database where a media service writes a unique frame with its ID, and another media service reads that frame with an ID. Now, this media database can be built with shared memory and fast networking. Now, the networking that we choose is actually a detail, and it's applicable to where this is deployed. If we're on premises, then we have We have technologies like Rocky 2, our DMA technology that we can use for that. If we're running in the public cloud, well, we don't have access to these technologies, but we have access to other fast networking technologies. So the choice of the actual networking doesn't matter. It's just the throughput that we need to achieve, and the system will run as fast as what the hardware can give us. So from this perspective over here, I want to highlight a couple of things. One, we can add as many hosts as we want in runtime. We can instantiate as many services as we want in runtime. And since these media services do not have any state in them, as soon as they spawn, they can start doing work for us. So they get their control information from the server that knows everything that's going on, and they can start contributing into the transfer fabric. But they don't know the existence of anybody else because the control applications actually just coordinating everybody. So in this system, there's built resilience because multiple services can be doing the exact same job, contributing into the fabric that just delivers frames when and where they are needed. Now, why is all of this important? This is important because all of a sudden, when we're talking about scale, when we're talking about how we can build things, well, one control applications can cover one system, can cover two systems or three systems, because all it's doing is just coordinating the work of many different media services. So if you could think of a large-scale application that requires 100 inputs, let's say 100 SRT inputs going into a vision mixer, well, there is no one single computer that can actually do that today. But what we can do is through a distributed architecture where we could instantiate as many inputs as we want, and all these inputs can be distributed on as many systems as we can afford to pay for, and we can frame accurately control all of this to make it appear as one system. So that means our software can span one computer, two computers, 100 computers. It's up to the system architect. So I'm going to share some actual numbers of a benchmark that we did on an implementation of this architecture. And the benchmark we chose was 5 mixers in series. And it's a bit of an academic example, but it still makes a point. So this is all done in 1080i 50, and we compare it to a theoretical latency of 200 milliseconds as a baseline using asynchronous interconnect, saying that's the minimum that is possible. So if we look at a single host architecture, everything running in one same computer, well, it goes lightning fast, obviously. So the measured latency is actually 6 milliseconds to do all this work versus what we expect with a traditional synchronous interconnect. That's about a 33.3x gain. Now, if we go into let's say we live migrate the light blue mixer to a different system. Well, right now what we're incurring is a network copy of uncompressed video data across the network. Do the work and send it back to host one. And with this, what we see is that we're actually at 15 milliseconds to actually do this whole pipeline, and the gain is 13.3x versus the benchmark. And this is even a more theoretical application of it, and say, let's add a lot of networking here. So a lot of networking here is actually migrating the light blue to a different availability zone. And if you've worked with availability zones, that's within a radius of 100 kilometers. So what we're doing is we're moving uncompressed video from about 100 kilometers or less in one direction, doing the work and sending it back 100 kilometers or less and outputting it. And we get 26 milliseconds, which is a 7.7x gain versus what traditionally would happen with the synchronous interconnect. And this is all done on the C6IN 8XLRs that have 50 gigabits per second. And there are more other tests, other things I could share with you, how we can saturate the network, et cetera, et cetera. But the goal of what we're doing is to really achieve the benefits of IT. And this is kind of the academic. We want to achieve the agility that we can, the scalability, composability, reliability, flexibility in terms of licensing, because we can decide what we want to use in runtime, and sustainability. Well, there's a lot of work happening in many different industries that we can tap into and then reap the benefits of that. So some parting words. We have to learn from other industries, use what they have achieved and apply it to our industry. And we can fuel our innovation on top of what they have done already. Now, I find it personally really insulting when somebody tells me that COVID proved that we don't need the quality that we're always striving for and the latency, and it's proved that it's actually all for naught, because I spent all my career building solutions that care about every single pixel. And I think as an industry, that's our claim to fame, that we know how to tell a story, and we know how to tell it properly, and we know how to tell a professional story. So I don't think the position to compromise on quality, on latency, on 24/7 reliability, all that is actually the way for our industry to move forward. We need to move forward without compromising our basic principles. The software transformation in our industry for these applications is an opportunity for every single person in this room and in this industry. If you're an end user or broadcaster, you can, with a click of a button, build a very simple solution where a single commentator gets 4 buttons and they're self-operating and they're able to make some content, and it's useful for your business. And with a click of another button, we can shut everything down and then build up another system that spans hundreds of inputs, full-blown gallery, and everything that we do is customizable. So from an end user perspective, you can guarantee that you're architecting your system, your capabilities to emerging market needs. And it means that you only pay for what you're actually using. It means that you have a lot more leeway and flexibility. So the future broadcast engineer is actually writing Terraform scripts, is building custom UIs that address the business needs that are actually required. And with that, we just widen the pool of talent that's available to us to actually work with us. If you're a system integrator, when we talk about customization, about tailoring, about DevOps, about custom UIs, well, not everybody has that capability or wants to head into that. Well, that's a fantastic opportunity for system integrators. If you're a technology developer, we've all built great technology that's all stuck, bundled in these huge monolithic applications, and it gives us a chance to breathe new air into that IP and make it available and useful in different formats. So with that, I will leave you with the exact same conclusion that I gave on the career day for the 3rd graders. And I said, do not become a firefighter, become a broadcast engineer, because it's really cool. Thank you.
Still have chance. Any questions? Andy?
Thank you. It's an inspiring presentation. You talk very generically, and I wholeheartedly agree with everything you said. There's obviously some specifics that you guys are doing in Metrox, and I wonder if you can talk about the openness, what level of openness the innovation you're doing in that space has.
Well, we have been building developer products for the longest time. We have APIs that we have been developing, and we started out this venture with APIs and making it accessible to whomever wants to deal with these APIs. Now we are having more discussions with other bodies in the industry to see what it means, how we can work together, what's the interoperability aspects of it, and yeah, that's where we are. Sure.
You talked about processing things sort of on a frame base.
Yes.
But when you actually look at a video stream, there is a lot of state between frames, and if I'm trying to do things one frame at a time, how do you share state information between frames?
What we're talking about, full granularity of a single frame. So for anything that's happening in this distributed environment, there's a control model that allows for every single frame, for every single processing unit to change. And that knowledge resides within the server, and we deal with control information as if we treat it as important data as if it's media. So the control information that's associated with that media gets transported and preserved associated with it. So there's a little bit more to it. I can go into details, but you could come see me afterwards. That's a whole discussion in itself.
Okay, I think we're out of questions and out of time. So thank you, and thank you all for your attendance today. I hope you appreciated the sessions, and we look forward to seeing you tomorrow morning. Thank you.